thinking about the scale of life within the known universe, we must consider aspects such as available resources, evolutionary strategies, mutations, and physical limitations of planets and celestial bodies. Simply put, is there an upper limit to the maximum possible size of living beings in a scientifically valid world without taking into account anti-gravity, force magic, and other physical concepts unknown to us? When we talk about life, we subconsciously mean organisms of all sizes, from cells and animals to fungi and trees. The largest creatures on Earth are record-breaking animals that have reached the maximum among their species in mass, height, or length. For example, gorillas, a genus of the largest primates, representatives of the suborder of primates. In adult males, growth can reach 2 meters. The width of the shoulders is 1 meter, and the weight reaches 250 kilograms or more. Elephant, the largest land mammal. Its length reaches 7 meters, and height 3.5 meters. The average body weight of an elephant reaches 12 tons. The blue whale, on the other hand, is the largest animal that has ever lived on Earth in terms of mass and length. The size of the blue whale is impressive. These giants reach 33 meters in length and weigh almost 200 tons. As you may have noticed, the largest animal on Earth lives in water, even when dinosaurs existed. And that's no coincidence. The fact is that the aquatic environment counteracts the force of gravity and reduces the mass of the object several times. Of even greater importance is the ultimate cohesive force of the particles that make up the body. It depends on the force of gravity. The greater it is, the smaller the limit. In marine animals, the mass decreases, so the limit of the cohesive force will be much greater. Also, for large animals to live on land, they need something to lean on. Land giants have strong, bony skeletons, developed limbs, and powerful muscles. They spend a lot of energy to overcome gravity and move their bodies in space. But still, let's try to enlarge a large animal by 10 times. Then the rigidity of the skeleton will increase by a maximum of 100 times, and the mass will increase by 1,000 times. Thus, the skeleton will not be able to support the weight of the body, leading to its non-viability and collapse. The proportional increase will also not last long. If we are pulling a living body in one dimension, the issue of metabolism becomes very relevant. After all, even trees have a limit to how high they can deliver nutrients. Which means that as the size of the planet and its gravity increases, so does the force acting on animal bones. But since gravity causes so many problems, why not change it by moving to a smaller planet? This approach would work, but only up to a point. Planets can't shrink indefinitely. The smallest planets will have a mass 10 times smaller than Earth's. Consequently, the largest creatures would be at most 10 times the size of Earth's. That is, on such a planet, we will meet a gorilla about the size of a 5-story building. However, there are minimum sizes for such planets as well. If it is smaller than 1/10 of the Earth's mass, it will not be able to hold an atmosphere, one of the necessary conditions for life. Yes, of course, you have to take into account that we are talking about organisms from planet Earth. They are, as we know, quite fragile. So we're going to move a little bit away from the classic Earth view and try to apply science fiction. So if it's more or less clear with planets, let's try to think about space or outer space, where gravity is almost non-existent. Imagine a life form in the shape of a giant medusa or space fungus that collects space dust in it to grow, using starlight both for its growth and to propel its biological light sail. To compensate for gravity, the creature will probably begin to rotate as it grows and will continue to add angular momentum as it gets larger and larger. The purpose of the organism is to balance gravity with centrifugal force. These creatures could theoretically grow to gigantic sizes if they were limited only by raw materials and solar energy. Perhaps they could infiltrate star systems and raid like Vikings on rings around planets, asteroids, and even small moons in search of resources, and then leave the devastated territory as they continue to grow. Perhaps they could reproduce by releasing spores, or more likely just split into 3 or more parts like cells. Would humanity become just dessert? Most likely, yes, no more than that. And what if we go even further without tying the organism to life on the planet, or even its orbit? After all, we can assume that a hypothetical living organism could be the size of, for example, an entire star system or even a galaxy. True, in such a case, there are even more problems. And the most important is energy and speed. Any creature must have some form of metabolism. The exchange of useful substances between different parts of the body is necessary for the transfer of energy. And in order to exchange that energy, we must first get it from somewhere. If our being is the size of a star system, then the only obvious source of energy is a star. So we have a kind of living Dyson sphere. Metabolism would be extremely slow. Otherwise, the substances would get enough kinetic energy to leave the system. What's unclear is how such an organism could have evolved in the first place. After all, natural physical processes tend to form planets from a field protoplanetary disk around a star. If such an organism exists, it must resist this process. But how is unclear. If we are talking about intelligent life, then the organism must form informational connections. In humans, these are brain neurons, which are interconnected by means of electrical impulses. But if the brain model is enlarged to the scale of a solar system, let alone a galaxy, then communication between neurons will still be limited by the speed of light. The speed of thought, the passage of an impulse from one end of the brain to the other, would slow by a factor of several trillion. In this case, to think as many thoughts as a human thinks in a lifetime, the supposed being would need trillions of times more time. He's got about 100 trillion years to think. A true philosopher on a universal scale. And yet, if the brain were the size of our galaxy, there would only be enough time since its formation for 10,000 messages. So it's pretty hard to imagine life forms comparable in complexity to humans occupying scales much larger than the size of a star. The next problem we have to face is cooling. Yes, a living organism needs cooling. Since the skin is responsible for cooling an animal, and heat is generated by volume, large animals cool less efficiently. Back in the 1930s, Swiss biologist Max Claiborne noticed that in the vast majority of animals, the rate of basic metabolism is proportional to body weight. Indeed, if heating rates were not reduced, large animals would simply boil over. However, if we assume that for mammals to function normally, the minimum metabolic rate must be this much, then we get a maximum body size of about 1 million kilograms, which is less than 10 times the mass of a blue whale. In principle, it is possible to imagine animals of even larger size. Relying on Landauer's principle describing the minimum amount of energy required for computation, and assuming that the energy resources of a supermassive multicellular organism are spent only on the slow reproduction of its cells. In time, we will see that the problem of its mechanical support overtakes the problem of heat dissipation and serves as a major limiting factor on growth. But at this scale, it becomes unclear what such a creature would do, and how would it come into existence. And of course, there is the view that the universe is the largest living organism with creaturely features, built from information and subject to processes of metabolism, adaptation, and natural selection. In this interpretation, the living universe hypothesis is consistent with the cosmological view that it can transform into other universes. The universe also grows. It is constantly expanding. New galaxies are formed, and eventually it will disappear when it exhausts all its energy. If this is the case, the question arises, what are we doing inside this organism? Thoughts on this matter are not the most rosy. Certainly, in broad circles, the idea that the universe is a living organism is philosophical and even fantastical rather than scientific. However, our understanding of the universe continues to evolve. And as new discoveries are made in various fields, such as quantum mechanics, astrobiology, and cosmology, our ideas about the nature of the universe may change. In conclusion, the question of how large a living organism can be in an ever-expanding universe continues to interest the scientific community. While physical constraints such as gravity and structural stability may limit the size of organisms at the biological level, The vastness of the universe offers endless possibilities for life to thrive and evolve beyond our imagined boundaries. Who knows what incredible life forms may exist in the depths of space, waiting to be discovered? The possibilities are truly limitless.